A solid ball rolls down an incline and does start from rest. At this point, we are recognizing that a rolling object is occurring and not just sliding. So we will need to do the law of conservation of energy, but keep in mind our kinetic energy might be different than what we're used to seeing. So we start from rest. We ask, do we have any gravitational potential? And the answer is yes. We are above the ground, or above the origin. Let's make the origin the ground level. This will be here. And again, we are studying for rest, so no kinetic energy initially. There are no springs attached, nor is there work done. So this is all gravitational potential energy. Okay, at the bottom, we would ask, is there any gravitational potential? And we'd say, no, we have returned to our ground level or our origin, so there's no gravitational potential. Okay, but is there kinetic? And yes, there is. There will be two kinds of kinetic energy. Kinetic energy translational, which is the kind we're used to doing. And now our new one, kinetic energy rotational. So I'll give a sub T and sub R for both of those. So we remember there are two kinds of kinetic energy. And still no springs attached. And then a small amount of thermal energy. Rolling friction is a very small amount of thermal energy lost, mostly as vibrational energy or sound. So we'll ignore that. Okay, so plugging into our equation what we know about these, we know that gravitational potential is mgh. Okay, that will equal our normal kinetic energy, 1/2 mv squared. And then plus our brand new equation, 1/2 I omega squared. Okay, for rotational kinetic energy. Okay, now we are going to substitute two things in, one for our I, one for our W. We have defined moment of inertia as equal to C mr squared. Reminder, C is the constant that might occur in front. For example, here we have 2/5 mr squared. So C would be 2/5. Other time we might have a 1/2 or whatever that would be plugged in for C. Now to plug in for the omega, we're going to remember that V equals R omega. The linear velocity is a product of the radius times angular velocity. Therefore, omega is then going to equal V divided by R. Down here, we'll substitute those in. So we have mgh is equal to 1/2 mv squared plus 1/2 cmr squared times the quantity v squared over r squared. Remembering that we have to square the omega, and we are substituting v over r for that. Okay, there's a mass in each of these expressions that can cross off. Okay, and r squared divided by r squared can cross off. So we're left with a simple equation, GH is equal to 1/2 v squared plus 1/2 cv squared. Again, the C is a constant that occurs in front of the mr squared and depends on what kind of object is rolling. Now for this question here, we have a height of 3.4, so G, we're going to go 9.8 multiplied by 3.4 equals 1/2 v squared plus 1/2. Now again, the C for a rolling sphere is going to be 2/5. Okay, and then v squared. Okay, you will then combine like terms with your v, okay, and then solve for it. V will come out to be 6.9 meters per second. And that's how we account for a rolling object going down an incline with no applied force. What we mean then is just the gravity force is what's responsible for rolling it down for this example.